This is Professor Speher from the University of Alaska Southeast, and this is a lecture on ecological economics, Chapter 4, Nature of Resources and the Resources of Nature, from the textbook Ecological Economics Principles and Applications by Herman Daly and Joshua Farley. Ecological economics challenges one of the goals of the neoclassical models, that of ever-expanding economic growth. Ecological economists do this by analyzing the benefits and costs of continued growth in the economic subsystem by asking the question, when do the benefits of growth begin to outweigh the increasing opportunity costs of encroaching on the sustaining ecosystem that growth entails? That is, when does the economic growth become uneconomic when the social costs begin to outweigh the social benefits? In this chapter, we begin to identify the costs of economic growth by obtaining a better understanding of what growth entails. Our goal and objective for this chapter will be to establish how economic production engages in processes that move the inputs of production from low entropy to high entropy, or from useful, ordered matter energy to disordered, useless waste. This will help us to explain and define the point at which the benefits of economic growth are outweighed by the increasing opportunity costs. We will also establish and describe what ecological economists mean by a finite planet more thoroughly and explain and describe the laws of thermodynamics. Finally, we will define and describe scarce resources using the vernacular of stock flow resources and fund service resources, and apply excludability and rivalness to these resources. In addition, we will apply this new vernacular to specific examples of scarce goods and services provided by the sustaining system, all of which will help us later to understand the often ignored real costs of economic growth. The economic system is a subsystem of the planet's ecosystem, and this perspective implies a big question for ecological economists. Just when is the economic system too big for the system that contains it? And when is it just big enough? And what policies will be effective in keeping the economy within this defined optimal size? It will be the ecological economist's job to identify and provide alternative policies necessary to keep the economy within this optimal size range. To do this, it is necessary to have a good understanding of the limits of growth, and then use economic tools to determine optimality given the established limits. Currently, the dominant tool for determining economic optimality is the market. However, markets only function effectively with goods and services that have certain specific attributes. For example, they don't really do a very good function at all with goods that cannot be exclusively owned privately. Using the market to allocate resources sufficiently requires private ownership of these goods. So one of the goals here will be to identify the specific attributes of goods and services that allow the economic market system to allocate goods efficiently, and then to address those goods and services that cannot be allocated efficiently by the market due to the problems inherent with the problems of ownership. We will deal with these types of goods and services in a different way. This chapter will help us gather a clear understanding of the specific attributes of goods and services that the market cannot allocate efficiently among alternative ends. Let's begin by trying to get a good understanding of the role of the limits to growth within the neoclassical model and the ecological economic model. Ecological economists assume that we face a finite planet. Neoclassical economists do not assume this and rely heavily on the saving grace of innovation and technology that they believe will allow and provide for ever-expanding economic growth. This is an explicit goal of the neoclassical model. But neoclassical economists go even one step further to suggest that it is growth itself that encourages countries to keep ecological damages to a minimum, and that growth is one of the best mechanisms to ensure preservation of ecosystems. They reason that it is the underdeveloped countries that tend not to be willing to preserve the environment, as they are too busy fighting for survival and do not care about the costs of the damages from growth. Only the industrialized developed countries can afford to address environmental concerns, and so it is argued that economic growth is not only possible, but it is good in that it encourages ecosystem preservation. The ecological economist, on the other hand, believes that economic growth cannot continue indefinitely. Consider, for example, a continuous annual 1% growth rate of the human population. This would result in a mass greater than the entire planet in just over 3,000 years. The economic system cannot grow indefinitely no matter how much we can substitute a new resource for an exhausted one. Eventually, we will run into the wall where technology may not be able to save us in time. There is a finite supply of inputs for which production must rely on, and as development encroaches on these sources of inputs while simultaneously requiring ever-expanding means of storage for the outputs of pollution and waste, limits to growth must become our mantra rather than a blind faith in technology. Relying on technology to save us every time we reach a limit to growth is much like playing Russian roulette. If we continue to play Russian roulette long enough, frankly, the numbers are just not in our favor. Addressing the limits to growth then requires us to determine when economic production becomes uneconomic, assuming it has not already done so. Let's look more closely at why we believe that infinite growth is impossible in the closed system that we live in. The branch of science most relevant to this issue, and indeed most relevant to the economic problem, is thermodynamics. Daly and Farley argue in this chapter that one of the main reasons that economists today cannot see or understand the limitation of continued economic growth is due to the way the history of the development of our economic discipline began. It began to grow as a discipline in the late 1700s. It developed during the growth in the field of physics, which began around the 1600s, and was heavily influenced by this model's success. The mindset of the physicist is that of an axiomatic mathematical system. It is a mechanical mindset that suggests that the world works much like billiard balls. Equal and opposite forces with well-defined laws that guide and determine outcomes given initial positions, forces, and velocity. And all the outcomes could be mathematically determined and even reversible if equal and opposite imposing forces were initiated. Given the opposite imposing forces, they could show and therefore predict that the original outcome would result. Axiomatic mechanical physics was the most developed and admired discipline at the time when classical economic model of the 17 and 1800s was in development, and they emulated this mechanical model. This mindset encouraged economists to take money and quantities and build up a quote-unquote logically consistent theory based on a set of fundamental axioms. These theories deduced by the economic axioms were then applied to the real world. It's important to note that these axioms and theories deduced at the time were not based on experimentation. Remember, axioms from an axiomatic system are thought to be a priori truths or knowable without any appeal to particular experience. This means that such models assume that all knowledge within the system proceeds from theoretical deduction based on a priori truths called axioms, rather than from observation or experience. There are a lot of problems with axiomatic models applied to a social science, but this textbook focuses on three specific problems. First, this mindset implies that our circular flow can continue indefinitely given the initial conditions and the initial axiomatic assumptions. There are no limits except disequilibrium that may take place within the system, but the system is assumed to be self-correcting, so this is not really a problem. Growth can go on forever as we continue the cycle around the circular flow diagram. Secondly, this mindset also assumes that there is no free will and that everything is predetermined given the initial conditions. Human action, thought, or gaming a system is impossible within this mindset because it's axiomatic and all theorems developed are always true given the rules of inference and the initial conditions, which are the axioms in all other theories, corollaries previously proved with the laws of inference. If everything is predetermined, then policy is irrelevant, as it can have no impact given that the initial conditions have already been initiated and the outcome thus predetermined. Now, in defense of mathematical economics, let it not be assumed that economists don't use empirical investigations. We have an entire field of econometrics that instructs students on how to do empirical investigations, but at the core of our discipline are a set of axioms that are assumed to be true and upon which our field has been deduced. Increasingly, however, these axioms are being questioned, and one such example is within the field of behavioral economics. But at the time that our field was forming, it modeled itself after mathematical axiomatic systems. But then, if we emulated mathematics and physics, how in the heck did the laws of thermodynamics manage to get ignored? Thermodynamics, after all, is a subfield of physics. The answer is that we really leaned heavily toward the mathematical discipline rather than physics. As William Stanley Jevons, a classical economist of the mid-1800s, argued, quote, "It is clear that economics, if it is to be a science at all, must be a mathematical science," unquote. Economics somehow was able to ignore the fundamental laws that came out of physics, and this impacted not just our models, but our mindset as well. Even though all human production must ultimately be based on resources provided by nature, and all of nature's resources, which are transformed through the production process into something of use to humans, requires work as defined by the laws of thermodynamics, these laws of thermodynamics and the impact that it might have on our economic model was completely ignored. Yet, only low entropy or free energy can provide work. All work performed and required by production processes requires low entropy sources, and the first law ensures that all work requires a transformation from low entropy to high entropy. It must be the case that all products and waste generated by an economy cannot just be extinguished, but must be accounted for as an integral part of the production process. This means that as nature is processed through the production process, we are taking low entropy inputs and excreting high entropy outputs, which includes both wastes and useful, and sometimes not so useful, human goods generated. As Daly and Farley put it, and I quote, "The entropy laws tell us that inevitably whatever resources we transform into something useful must disintegrate, decay, fall apart, or dissipate into something useless, returning in the form of waste to the sustaining system that generated the resource in the first place," unquote. The economy is better defined as an ordered system for transforming low entropy raw materials and energy into high entropy waste and unavailable energy, and thus work. The infinitely circular flow diagram fails to capture this important fundamental truth and mindset. According to the law of entropy, or the second law, the world must move toward greater homogeneity as energy and work is used up in the production process. And the first law tells us that entropy is a one-way, irreversible change. A great example might be that of a forest. Many believe that a forest is renewable. Cut down the trees and plant new ones. Yet it is important to understand the distinction between a tree farm and a forest. A forest is an ecosystem with a complex network with an interconnected system that contains a biological community that interacts with organisms and lives in a complex physical environment. A tree farm is an acreage of land with trees planted on it to replace the ecosystem that was destroyed by logging. Tree farms preserve trees, not an entire ecosystem. The forest has undergone a process of moving from low to high entropy, a one-way process. It is argued that lumber is not best considered a renewable resource, although a tree can be replanted. We are not renewing a forest. We are creating a tree farm and destroying complex, interconnected ecosystems. But perhaps to an economist who is very good at mathematical analysis and is not able to calculate the cost of a lost ecosystem or the benefits of preserving an ecosystem, while the cost of cutting down a tree and replanting a tree and then selling the lumber, which improves the GDP, is easily mathematically determined. It appears that the benefits of an ecosystem is not easily evaluated, but cut lumber for housing and growth is easily calculated. If you can regrow a tree and produce more lumber, the value of this improves the gross domestic product, GDP, and thus growth, while the benefits and value the ecosystem provides us is not easily evaluated. So instead, we view trees as a renewable resource with little understanding of the long-range consequences on the economy. This is an economic model with little understanding to what extent it is dependent on the larger global ecosystem that contains it. That a tree farm acts upon the GDP while a forest does not means that ecosystem preservation does not improve economic growth by increasing the GDP. And since we do not care about the laws of thermodynamics and only have the picture of the circular flow diagram, it seems like cutting trees and selling lumber might actually be a real renewable resource, allowing us to go around the circular flow diagram again and again without any consequence to our forests and our well-being. And social welfare to this economist has actually improved because the GDP improved and economic growth means more for everyone and therefore everyone is better off. But we know better. Ignoring the laws of thermodynamics and economic models does have a very big impact. Let's review what these laws really tell us, and let's do this by understanding how these laws were uncovered. The first law was discovered when it was realized that a temperature differential was required between two sources in order for work to be performed. Remember, work in thermodynamics is energy transferred by the system to its surroundings. The transfer is fully accounted for solely by forces exerted on the system by external factors. Energy cannot be created or destroyed, and the performance of any work from the energy transfer requires a differential temperature between two sources, and the greater this differential, the more work that can potentially be performed. But the second law established that energy moves inevitably towards homogeneity. This is the law of entropy. For example, a body of hot water mixed with a body of cold results in the hot water moving toward the cold while the temperature differential declines or dissipates and becomes homogeneous. This means that energy becomes increasingly unavailable to perform work because the temperature differential dissipates. The differential in temperatures is called work. It was later established that energy was work and defined through the famous Einsteinian equation E equals mc squared. In fact, entropy really is just a measure of the unavailability of energy to do work. And importantly, entropy is a one-way street. It is a direction of irreversible change, a continual increase in disorder in the universe. This one-way mindset that the production process actually relies on is moving from low entropy toward high entropy or disorder, with less work available for continuous production. This mindset is much different than the infinite circular flow mindset of the neoclassical model. Did our science take a wrong turn in history that is now leading us down a path to perdition with its fundamental need to maintain infinite economic growth? Are we turning our planet into tree farms without any appreciation of the consequences of the law of entropy and its impact on complex ecosystems necessary for the continued existence of all life forms on Earth? This has important consequences for any economic model or theory. We have finite supplies of energy, finite supplies of raw materials, finite absorption capacities for wastes, and very complex and poorly understood, yet finite capacities for ecosystems that act as important services in the production process, and many services that nature provides that is essential for our survival. With continued growth in production, the economic subsystem will eventually overwhelm the capacity of the global ecosystem to sustain it. Let's ask a different question. Can economic development grow indefinitely? Now, by development, we mean the increase in quality of goods and services as defined by their ability to increase human well-being, provided by a given throughput. Development implies any movement toward an improved, not necessarily larger, economic system. What we mean by this is an increase in the quality of goods and services or an increase in well-being for a given unit of throughput. Is it possible to expect that human society can continue developing, perhaps only by ending growth, but can we expect to continue developing for an indefinite future? Now, keep in mind that many desirable ends require few physical resources. Exercise, walking in the wilderness, the company of good friends, just the knowledge alone that ecosystems are not being continually encroached upon and that we are in the midst of a sixth greatest extinction event with as many as 30 to 50% of all species possibly heading toward extinction by mid-century, which is caused almost entirely by us humans. Frankly, just knowing that we're trying to stop this event increases the quality of my life significantly. We distinguish this from growth, which is a quantitative increase in the size of the economy as measured by the GDP and an increase in throughput. We will be drawing the distinction between these two terms, economic growth and economic development, continually in this course and expand more on what we mean by economic development later. We now turn our attention to an important distinction between different types of scarce resources, too often neglected by conventional economists, that of stock flow and fund service. We will begin this conversation in part 2. Until then, this is Professor Spihar at the University of Alaska Southeast.